Howdy everybody, I started this video and they came on with the announcements, so I'm going to see how far I get before the bell rings. So we're talking polynomials, and to begin with, when we talk about odd degree versus even degree, let me make the distinction. An odd function, we define a function to be odd if it has symmetry over the origin. So what that would mean is if I had a point, let's pick a new color. If I had this point, say this is the point 2, 8, notice 2 cubed is 8. And then I have the point over here, this is negative 2. If I have a negative times a negative times a negative, it's still negative, and that's negative 8. This point has been rotated 180 degrees. It's been reflected. It's got symmetry with respect to the origin. That's not the same thing as saying an odd degree. If a function has an odd degree, it could do all sorts of crazy things. It could just be y is equal to x to the 5th plus x to the 4th plus x to the 3rd. I don't really care what all there is, but what makes it an odd degree is that the biggest one right here is odd. And so that could look something like that. Okay, where this obviously does not have symmetry with respect to the origin, but it still is an odd degree function. I'm not saying these two are the same. I didn't even bother graphing that. Point being, there's a difference between an odd function and an odd degree function. Likewise, an even function, just because a function is even, that means that f of negative x is equal to f of x. That's not the same thing as saying an even degree, because an even degree would be something like y is equal, or f of x, or whatever, is equal to x to the 6th plus x to the 5th plus x to the, I don't really care. The fact that this largest exponent is even makes it an even degree function, but not an even function. Okay, so coming back here, if it's an odd degree and has a positive leading coefficient, the positive leading coefficient is going to make it, so then it's going to do something like this, where it ends up, the positive leading coefficient tells you how it ends. As x goes to positive infinity, y is also going to go to positive infinity. So what we'll write is we'll write our end behavior as x goes to infinity, f of x, y, whichever you prefer, goes to positive infinity. And then as x goes to negative infinity, that means what happens as x goes this way towards negative infinity, notice the y value is going to negative infinity also. So as x goes to negative infinity, f of x goes to negative infinity. If it's an even degree, then it can do all sorts of stuff here. It could do all kinds of, I don't really know what kind of crazy things it might do, but they end up both going up to positive infinity on either end of that. So with the positive leading coefficient. As x goes to positive infinity, f of x goes to positive infinity. As x goes to negative infinity, f of x also goes, f of x still goes to positive infinity. The negative leading coefficient is going to do the opposite. So it could do something like this. Oh, well, pretend that looks a little too linear. My bad. But this is as x goes to infinity, f of x goes to negative infinity. And as x goes to negative infinity, f of x is going to go to positive infinity. An even degree would do something like that. Okay, so as x goes to positive infinity, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to negative infinity. And so even in odd, they could have multiple, this one right here appears to have 1, 2, 3 zeros, and so it's probably cubic. This one has 1, 2, 3, 4, 5, 6, so it's probably degree 6. It doesn't necessarily have to be, but that's the idea of what we're looking at here. Okay, the next thing is when we talk about the multiplicity. So a multiplicity of 1 just means that I have a factor that shows up in my problem one time. So something like, if I have y is equal to x minus 1 times x plus 2 times x minus 3. Each one of those is raised to It's an understood raised to the first power. Well, we don't write that, but that tells us, that gives us that multiplicity. So in this particular problem, I've got a 0 at positive 1, I've got a 0 at negative 2, and I've got a 0 at positive 3. Since its leading coefficient, if I were to multiply all this out, since its leading coefficient is positive, it's going to come something like that. And what happens was the multiplicity of 1, it just passes through. I'll say pass through. So it just passes through the x-axis. It does, and just kind of keeps on going about its business. An even multiplicity is where I have something like y is equal to x minus 2 squared. And then I could even have an x plus 4. Where that doesn't have an even multiplicity. So if we were to do something like this one right here is the 0 that's going to have an even multiplicity, a multiplicity of 2. What that does is it bounces. Okay, and so on this one, we've got a 0 at 2. We've got a 0 at 1, 2, 3, 4, negative 4. Pretend I can draw. It's going to, this is positive, so it's going to end up going in the positive direction. It's going to bounce here, and it's going to do something and then come down like that. And this one, this is the 0 that has an even multiplicity. This one over, this one right here still has a multiplicity of 1. Okay, I want to get rid of that. There it goes. An odd multiplicity greater than 1, this is where it will bend. So you could think about the parent function y is equal to x cubed. That one kind of bends here at the origin. So it could be, but it could be somewhere else. We could have x minus 2 cubed. We could even have an x plus 1 squared. So if we were to graph this, we have a 0 at 2, and we have a 0 at negative 1. This one's it's got a positive leading coefficient, and it's got an odd degree. So it's going to start down here somewhere and end up here somewhere. Okay, so that kind of helps me. And then I know that at 1 it bounces. And then here, okay, this is hard to draw. So I kind of come like this and then go like that. Oh, okay, that looks really terrible. Sorry. So kind of do that sort of thing. This one right here is the odd multiplicity that came from here. And so that is a bend. I think the bell is about to ring. The next thing I want to do, I'll make a second video, and we're gonna match these equations with these graphs, and then we'll talk through these last little two. So we'll see when I can get that made for you. And good luck. Go practice.